today I'm going to talk about retrieval and retrieval augmented generation. So if we look at our standard prompting flow, normally what we do is we combine together a prompt template with an input. So if we say, please answer this question, I think Vin Diesel has been a voice actor for several characters in TV series. Do you know what their names are? We could get a response from a language model, but there's several problems with this. The first is accuracy issues. The models generally have a knowledge cutoff, so the parameters are usually only updated to a particular time. So, for example, if a new Vin Diesel TV series comes out, then the model that was trained up to a certain time point won't be able to know anything about it. There's also issues of private data. So data stored in private text or data repositories is not suitable for training for a number of reasons. Number one, it's not available to particular language model training providers, such as, OpenAI or Google or anybody else like this. The second thing is access control issues. So even if you're within an organization that has lots of private data and you can train a language model on that, certain people in the organization may have access to certain varieties of data and other people may not. So it's not just solely an issue of third-party providers, it's an issue of organization-level access control in general. In addition, there are learning failures. So even for data that the model was trained on, it might not be sufficient to get the right answer. And this is particularly the case for very, very large training data sets and models that are, modestly sized, because the models very often won't be able to learn from a single look at a particular fact or whatever else like this, especially if it occurred early in training. Another thing is, even if the answer is correct, it might not be verifiable. So you might want to be very sure that the model is not making any accuracy problems. And so in order to do that, very often a human will want to go back to the source of the data. So to solve this, there's a method called retrieval augmented generation, which will also be the topic of our second assignment here. And the way it works is you retrieve relevant passages efficiently, ones that kind of entail the answer to a question, and then read the passages to answer the query. So we have documents like this. We have a query. Based on the query from retrieval, we get a whole bunch of passages. We do reading, and then we get the answer. So this is in fact implemented in many or even most language modeling providers, including OpenAI. So to give an example, I asked the question that I just said about Vin Diesel's voice acting in TV series, and ChatGPT gave me an answer, and you can see that ChatGPT's answer includes several places with quotes. They're the little blue quotes there. And if you click on the quote, it tells you where the information source came from. And so this one says, behind the voice actors, Vin Diesel, and behind the voice actors, TV shows, Big Mouth Vin Diesel. Now, if we look closer into this answer, we'll see that it's not perfect, even though it is performing retrieval augmented generation. So, for example, I only asked about TV series, but it's giving me lots of things about movies, where it says Groot in Guardians of the Galaxy Volume 3, 2023 movie. And in fact, Vin Diesel was not even voicing a character named Groot here, so that's definitely an accuracy mistake. And separately, there's a place where it says, additionally, though the website for Big Mouth lists Vin Diesel, it appears to be a misunderstanding or error, as Nick Kroll is credited as the voice of Vin Diesel in that show. So there, actually, Nick Kroll was acting as Vin Diesel, but that's kind of a misunderstanding of the reader model. But anyway, you can get the general idea here. You can also see that it's not perfect, even for very strong models like GPT-4. So now I'd like to go into the actual methodology that we use for this. We have retrieval methods. And for the retrieval methods, we have quite a few different options. I'm going to go through each one of them at a time. So sparse retrieval, document level dense retrieval, token level dense retrieval, cross-encoder re-ranking, and black box retrieval. So black box retrieval, I'm not really going to go into it a whole lot. Basically, this is just asking a black box search engine to retrieve the relevant context and getting the top several results. Nonetheless, this is a pretty reasonable method to do it if you want to do search over lots of data that exists on the internet already. And that, in fact, is what ChatGPT does. It looks up on Bing by generating a query to Bing. So anyway, let's go into the actual methods that you develop and control yourself. So the first one is sparse retrieval. And the way this works is you express the query and document as a sparse word frequency vector, usually normalized by length. And so if I ask a query, what is NLP? We get a vector where each row of the vector corresponds to a different token. And we asked, what is NLP? And so the places for what, NLP, and is will all have a non-zero value, and everything else will have a zero value. And we also normalize by the length of the vector. So we get something like 0.33, 0.33, 0.33. Then we have a whole bunch of documents. So the first document says, what is life? Candy is life. Someone really likes candy. We also have another one that says NLP is an acronym for natural language processing. So this is a pretty good, answer to our question. Then we also have, I like to do good research on NLP, which is, a nice sentiment, but not a very good answer to our question, I guess. So if we look at the vectors here, we have what and candy and is have a fairly high score. And we have here NLP and is have a high score, and NLP has a non-zero score. So based on this, we find the document similarity with the highest inner product or cosine similarity in the document collection. And so if we take the inner product between these vectors, we actually see that the first one got the highest score because of its relatively high values for the words what and is. So as you can see, common words like what and is can get a high score kind of regardless of whether a document is very relevant. And so one way we can fix this is through something called term weighting. And the way that term weighting works is, in addition to having this vector that calculates the frequency within a particular document, we also have an upweighting term that gives higher weight to low frequency words, because low frequency words like NLP tend to be more informative about whether the document is relevant than high frequency words like what it is, because these high frequency words like what and is could happen kind of regardless of whether the document is relevant to the particular terms the person is asking about. So one well-used and easy to understand version of this is TF-IDF, or term frequency in document frequency. So the way we define term frequency is exactly what I talked about before. So it's basically the frequency of the term T in the document D, normalized by the total term frequency within the document. So that's what I already showed in the previous slide. And then in-document frequency is a little bit more involved. But basically, the way this works is we have log of the total number of documents in the collection divided by the total number of times this term appeared in any particular document. And so if a term appears many times in any particular document, it will have a low IDF score, one that's close to zero. But if it rarely appears, it will have a high IDF score. So basically, this is upweighting our frequent terms. And then for TF-IDF, we basically multiply these two terms together, and we upweight the low frequency words. There's another version of this called BM25 that is widely used. This is more involved, so I'm not going to go into all of the details, but basically, if you remember back to the lecture on count-based language models, there were a bunch of smoothing techniques for these count-based language models. And this uses kind of a multiplicative additive smoothing term to upweight things instead of using the term frequency. And the actual formula is here. K and B are kind of hyperparameters. And average DL is average document length. The details of this are not really important, but basically what you should know is that this is doing some smoothing on the term frequencies. And you can look in more detail if you're interested. So now that we have this sort of term-based sparse vector, we would like to use this to look up relevant documents in a collection very quickly. Because, we might have a collection that's extremely large as the entire internet, like what Google is doing when it searches. And so in order to solve this, we need a data structure that allows for efficient sparse lookup of vectors. And so we have all of these sparse vectors like this. And we basically turn this into an index where we have something like a Python-style dictionary or map that has as the key each word we would like to look up, and is the vector the corresponding index of that document. So for example, what in our case here only appears in document 1, so it would point to document 1. Candy also appears in document 1, NLP appears in 2 and 3. And so you can create this index like this. And this is called an inverted index. This is an important application, of course. So there's lots of software. The most kind of canonical software for this is Apache Lucene. So if you want to build a big index to look up vectors using this sparse index like this, you can take a look at Lucene. So the next thing I'd like to talk about is dense retrieval. And the way dense retrieval works is you encode the document inquiry into a dense vector and find the nearest neighbor. In order to do this encoding, you can use a number of things. You can use out-of-the-box embeddings, or you can use learned embeddings specifically created for the purpose of retrieval. And so what we do is we take all of these documents here. We convert them into embeddings using whatever embedding method that we want to use. We then have a query, and we take that query and we match it and find the nearest neighbor here. So if you're just using out-of-the-box embeddings, you don't need to do anything special for retrieval. You can just take your favorite embeddings like the SentenceBERT embeddings or the OpenAI ADA embeddings or something like this. But actually, the type of embeddings you need for retrieval are kind of very special. And because of that, it's important to, if you're very serious about doing a good job of retrieval, it's important to use embeddings that were specifically tailored for retrieval. And the reason why it is important to do this is several-fold, but the most intuitive way to think about it is if we think about the things that TF-IDF does. TF-IDF is giving a very high weight to contentful words and rare words. And we're not guaranteed that any random embedding that we get is going to do that. So for example, if we just take the average word embeddings of every word in a sequence, it's going to give the same weight to all of the words in the output. And in fact, common words tend to have slightly higher norms than infrequent words. And so that would actually upweight common words, which is kind of exactly the opposite thing we want. So how do we learn retrieval-oriented embeddings? The normal way we do this is we select positive and negative documents and then train using a contrastive loss. And so an example of this is we have a query, and then we have negative documents for that query, and we have positive documents for that query. and we formulate a hinge loss or maybe some sort of probabilistic loss similar to the hinge loss, and do fine-tuning of the embeddings. So if you have gold standard positive documents, then this is relatively easy to train because you just need the positive documents, and then you can get negative documents in a number of ways. One common way of getting negative documents is you just form a batch of data. And given that batch of data, you take all of the other documents in the batch, all of the documents in the batch that are positive for some other query, and you use those as negative documents. So you sample 32 query document pairs, you use the aligned ones as positive documents, and then use the 31 other ones as negative documents. And this is both effective and efficient because you can kind of learn from the query document pairs all at the same time in an efficient implementation. However, this is not enough in many cases because that will end up having lots of very kind of obviously wrong documents because, they're documents that are relevant for a completely different query, and it's kind of easy to distinguish between those. You can just look at superficial word overlap. So another common thing to do when you're training these models is to get hard negatives. So hard negatives are basically negative examples that look plausible but are actually wrong. And so here, this famous method called DPR it basically learns the encoders based on both in-batch negatives, like I mentioned before, and hard negatives that were created by looking up documents with BM25. And so the ones that were looked up by BM25, kind of look very similar superficially, but they might have, subtle errors in them for why they're inappropriate. There's also methods to learn these retrievers based on kind of not supervised data. So one major bottleneck, if you're taking the positive documents from human annotations of whether something is correct or not, or human click-through logs, or other things like this, is that you need that data in order to start training a model. So Contriever is another method that uses two random spans within a document as a positive pair, and random spans from across documents as negative pairs. And so this can be used for, very, very large scale initial pre-training of the models. And then after you've done that large scale initial pre-training, you can then go in and fine tune it on, actually annotated data to improve it further. Okay, so we've talked about training these dense product models, these models that look at dense embedding overlap for nearest neighbors. But the problem is, in order to calculate this, you would need to calculate it over a very, very large document base. And just taking a product between the query and all of the other documents in the document base is extremely costly. And so in order to fix this, there are methods for approximate nearest neighbor search. And these are methods that allow you to retrieve embeddings that have the maximum inner product between them in sublinear time. And because you're doing the maximum inner product, this is also often called maximum inner product search, or MIPS. So I'm going to introduce on a very high level two common methods to do this. The first one is locality sensitive hashing, or this can also be called kind of inverted index as well. And what you do is you make partitions in continuous space, and then you use it like an inverted index. So let's say we have a whole bunch of embeddings. I demonstrated two-dimensional embeddings here, but in reality, this would be, as large as your word embedding, your query and document embedding space. So this would be, 512 or 1024 or something like that. And what you do is you define a whole bunch of planes that separate these points into two spaces. So if this is our first plane, all of the points above the plane will get a 1 for this partition, and all of the points below the plane will get a 0 for this partition. And we do it similarly. We create a whole bunch of them. And then based on this, we can now assign sparse vectors depending on each of these planes. So we have, for example, the top one, 1, 0, 0, because it's on the right side of the blue plane and the wrong side of the red and the green planes. And then for the top right, we have 1, 0, 1, because it's on the right side of the blue and the green planes and the wrong side of the red plane. And so based on this, now we have a sparse vector, and we already know what to do with the sparse vector, right? We look it up in an inverted index, just like we did for a sparse, sparse lookup table. So that's one method. Another method uses a graph-based search. And the basic idea behind this is that we create hubs. And these hubs are kind of a small number of points that are close to other points in the space. And so we create some hubs and then we search from there. So if we have a similar looking set of points in the space, we find these hubs, which are something like cluster centroids. And then based on the cluster centroids, we then rule down, or we greatly reduce the number of points that we need to be looking at. And then we search through only those points in a more kind of extensive manner. And you can even turn this into a tree where you have hubs and then you have kind of mini hubs and then you have all the points. So this allows you to do a kind of tree-based or graph-based search. So obviously, unless you're really excited about these algorithms, this is something that you probably don't want to be implementing yourself. And the good news is there's lots of very good libraries that help you do this. In fact, there are so many libraries, it's hard to manage them. But some libraries that people very commonly use, I think FAISS, FAISS, is a widely used one created by Fair in Meta. And ChromaDB is a separate one that is kind of an AI native embedding search database. So both of those are good options. Even with intelligent training of dense embeddings, however, there still are problems. And the biggest problem that you face when you're looking at something like cross-encoders, when you're looking at dense embeddings, is that in order to form a good dense embedding, you need to kind of know in advance what you're looking for, right? Because you're taking a long document, you're condensing it down into a single embedding, or a long passage, and you're condensing it down to a single embedding. And so if during that condensation process, actually there's other information that is relevant to a query, but you have to throw out because of the limited embedding capacity, this causes you to, essentially fail at doing retrieval appropriately. So there's a couple methods that can be used to fix this. So the first method is, in contrast to the bi-encoder, which is what I've been talking about at this point, where you kind of do full encoding of queries, full encoding of documents, and then do inner product search for a score. You can use a cross-encoder. And the way the cross-encoder works is you append the query and document, and then you run them through a model like a transformer model, and you calculate the output score. So the problem with this, this is great because it gives you maximum flexibility. Transformer models are powerful. You can assess relevance very well. The problem with this is this precludes approximate nearest neighbor lookup, because now you're running through many, many nonlinearities here. So this really can only be used for re-ranking documents, or even if you're doing retrieval over a very, very small number of documents. But if you really want maximal accuracy, I definitely would recommend doing something like this, because it can allow you to do kind of a second pass filtering over the most relevant looking documents to identify the ones you really want to add to your context. So then there are also approaches that are kind of in the middle of these two. The most famous one is Colbert. And I called this token level dense retrieval. It's also called late interaction in the Colbert paper. But the way it works is you use contextualized representations of all query and document tokens to compute a retrieval score. And so you do offline indexing of every token in the document. And then based on this offline indexing of every token in the document, you then have a query encoder and you do matching between each token in the query and the highest scoring tokens in each document. And the reason why this is good is it still allows you to encode all of the tokens in the document, but each of these similarity searches is still just a kind of maximum inner product search. And because of this, this allows you to do each of these searches efficiently and doesn't preclude you from running it over an entire database. The downside to this method may already be obvious, but in the traditional bioencoder, we have a single vector for each document. But here we have one vector for each token in the document. So basically, your vector database gets n times larger, where n is the number of tokens in the document. And there are certain methods to make this better, like you can compress each document to a smaller number of n, but still, this is definitely going to be more costly than looking up each token. So this is definitely something to consider if you want to get, very good scores, and Colbert is a good implementation of that to start with if you're interested in trying it out. So this is a final thing. This is something that is a little bit different than all the other things I talked about before, but I've used it myself and it actually can be pretty effective. It was also made at CMU, so by Liu Gao, so I would like to promote our CMU work, of course. But the idea behind a hypothetical document embedding is that it's actually somewhat difficult to match a query and a document, right? Because a query is a very short, possibly ungrammatical output that's asking a question. And then a document is a very long output that's written in a different prose style, and it might have lots of irrelevant information or boilerplate or fluff or something like that. So the idea behind a hypothetical document embedding is that it's easier to match a document in a document than it is to match a query in a document. But the input to our model is a query, right? So what do we do? And so essentially what we do is we then take a large language model, we feed it in a query in a prompt and say, generate a document that looks like it should be the answer to this query. And so then the LLM goes in and it generates a document, and hopefully this document looks more similar to the documents you want to retrieve than the original query does. And I've actually found this to be relatively effective at improving accuracy on kind of difficult tasks, especially ones that are out of domain from the trained models that I'm using. So I've gone through a whole bunch of methods, and I would like to finish up this section by giving some insight about which one you should be using. So my impression right now is that a good baseline to start out with is something like BM25. It's very easy to start out. And compared to embedding-based models, it tends to be relatively robust to new domains. So if you have a new domain, you're more or less guaranteed that BM25 will give you some performance, whereas embeddings may be really good, but they may be really bad, depending on how out of domain that is compared to your underlying embedding model. So, however, if you want to get the highest accuracy, definitely tuned models are going to be better. And if you're not worried about computation efficiency, using something like Colbert with kind of the token level retrieval will definitely give you good accuracy here. However, there's better support for bioencoder style models in kind of standard vector databases like FICE and Chroma and other things like that. So if you want a kind of easier method to get started very quickly, then using a bioencoder is probably the best way to go. Okay, so now moving on to actual retrieval augmented generation models. We have retriever reader models. And the way these work is you basically, the simplest way they can work is you basically just chain retrieval and reading together. So you use an out-of-the-box retriever and an out-of-the-box reader model, and you have your query. You could, for example, look something up on Google, get a whole bunch of passages, and then feed them into a GPT model and get an answer. This overall is quite effective. It's easy to implement and it will give you decent results. So definitely it's something to be worth thinking about. For assignment 2 in the class, you're required to only use kind of public models or open source implementations. So you could still replace that with Apache Lucene and then any standard LLM. And that could be, Llama Chat or Mistral or Mixtral or something like that. So you could definitely feel free to do something like that. Of course, the passages are concatenated to the context. And so because the passages are concatenated to the context can get relatively long and expensive and other things like that, but it's just something you have to deal with when you're using RAG. There are methods also for retriever and generator end-to-end training. So this is the paper actually where the name RAG came from, and I'll use that as an example here. But basically, there are several methods that propose to train the retriever and reader to improve accuracy. And specifically, the RAG paper by Lewis et al., the way it trained the reader was to maximize generation likelihood given a single retrieved document. And for the retriever, it maximized overall likelihood by optimizing the mixture weight over documents. So here's kind of a schematic, which is you have your query encoder, you run the retriever with maximum inner product search. It gives you several documents, and each document has a score. And then based on the documents and the scores, you generate with each document in the context, and then sum together the probabilities multiplied by the weights. And I have the actual equations here because I think it'll be a little bit easier to understand after looking at the equations. So generation is a mixture model, and you pick a document and generate from the document. This P eta Z given X is the probability of picking that document given the query X. And then this P theta X, Z, and all of the previous tokens is basically the probability of the next token given that you have this particular document. So you can see that this is basically linearly interpolating between the multiple documents. And if we look, this can be considered the retriever and the generator, the retriever and the reader. One really important thing here that enables end-to-end training is they have this probability of the retriever be based on embeddings. And so here we have the document embedding and the query embedding. And the probability is proportional to the inner product of these exponentiated. So you're basically taking a softmax over the inner product between the two. And this adjusts the retriever to give higher similarities to helpful documents. And So because the probability of the retriever model here is included in the end-to-end probability, you don't actually need any annotations about which documents are useful. You can just train all of this end-to-end and let backprop do its thing to update the retriever as well. One important issue when training models like this is that the search index will become stale. So what do I mean by this? If we go back to our previous thing about dense models, creating this blue search index on the right side of the figure here is very costly. So like, let's say you want to embed 1 million documents or 1 billion documents if you're a big search engine company. So doing this is very slow. And in contrast, doing lookup with kind of these approximate nearest neighbor searches is sublinear time or even, log time, so you can do it relatively quickly. So it's fine to do lookup over this big index, but if you start updating this document embedding, you need to recreate the entire index, and that would be, very computationally costly. So the solution to this proposed in this RAG paper by Lewis et al. Is we only train the query embeddings and we keep the document embeddings fixed. There's other alternatives like there was a paper called Realm from early in retrieval-based modeling. And in that method, they basically had an asynchronous process that was going through and using the most recent document embedder to re-update the search index during training. But that is, kind of a very onerous process. So I think it's quite common to use kind of a fixed document embedding and update only the queries. Another thing to think about is when do we do retrieval? So there's a bunch of different methods. The RAG paper that I mentioned before did this only once, right at the very beginning of generation. It grabbed a single document and then generated the entire output. This is the default method used by most systems. However, there's other options as well. You can retrieve several times during generation as necessary. And the way this works, you can do this either by generating a search token saying that we should start searching, or searching when the model is uncertain. And another way is to do this every token. So we can do this by finding similar final embeddings and using this to influence the probabilities, or approximating attention with nearest neighbors. So I'm going to explain about each of these in a bit more detail later. So triggering retrieval with token embeddings was proposed by Toolformer, Schick et al. And the way it works is you generate tokens that trigger retrieval or other tools. So in this particular method, it had several tools, including asking a QA model or getting a calculator or having a machine translation system. But with respect to retrieval augmented generation, it had this essentially wiki search functionality that would look up something in Wikipedia and then use that to influence the final probabilities. And the way this was trained is training was done in an iterative manner, where it basically generated kind of examples of tools being useful. And when the tools improved the probability of the following output, then that would be kind of treated as a positive example and used to further train the model. So this was really influential. And in fact, this is how things are implemented in ChatGPT nowadays, not only for doing retrieval, but also doing other tools like, for example, generating code or generating images or other things like this. Another option is to trigger retrieval with uncertainty estimates. So FLAIR, this is a paper by my student, Zhengbao Zhang. where we tried to generate content and then do retrieval if the language model certainty is low. So here's a schematic of how this works. But basically, if we have some retrieved documents, we can say generate a summary about Joe Biden. And when it generates a summary, maybe for the first output, the language model has high confidence. And because the language model has high confidence, we just generate the output. However, in the next step, it might generate something like saying Joe Biden attended the University of Pennsylvania, where he earned a law degree. But the model might not be very certain about this. It might have a low probability of certain important entities. And so based on this, we then form a query where what we do is essentially we blank out the low probability parts of this, and we do a search. And so this is also a little bit like the hypothetical document embeddings method, where we basically create a document that we think will look similar to the document that we want to find. We use that to create search results, and then we generate the output. And then we continue doing that, and whenever we have a high confidence output, like the one here, we don't do any retrieval. We just generate directly from the parameters of the model. But whenever we have low confidence outputs, we do the retrieval and base the output on this. And so I think this is a nice method that could potentially be used. The downside to that is you might sometimes need to generate twice, because you would generate the output once and then find the low confidence parts and generate again. But if you really care about the kind of quality of the output, this is, I think, a reasonable thing to do. Okay, so now moving on to the token by token retrieval methods. The kind of original, or one of the methods that popularized this idea of token by token retrieval is something called KNN-LM. And the way it works is it retrieves similar examples and then uses the following tokens from these examples. And this is kind of like a very powerful count-based bigram model in a way. So if you remember back to when we were talking about count-based bigram models, what we would do is we would take the previous token and we would calculate the probability of the next token by summing up together all of the next tokens and dividing by the total number of times that previous token occurred. And so given that background, we can talk about how the KNN-LM works. So we have the text context, X, and we want to generate a target output. Separately from this, we have all of the training contexts. So this is all of the contexts that appeared in our training data. And we encode all of these training contexts specifically by calculating the representation of the final layer or near the final layer of the model. And so we encode that as representations. Separately from that, we remember the next word that appeared after this context. So now we have a data store consisting of representations in next words. We then take the representation of the current context and we calculate the distance between the current context and all of the other similar contexts in the database. We take the nearest K. So we take the top K examples here, which would be Hawaii, Illinois, and Hawaii. We then do some sort of normalization based on the distance. And this gives us a probability distribution over all of the next tokens. Sometimes these tokens are duplicated multiple times. And so we aggregate all of these counts to be Hawaii, for example, 0.8 and Illinois 0.2. And then we interpolate this with the probability given by the standard language model using an interpolation coefficient lambda. And this gives us our final probability. So the nice thing about this is this allows us to explicitly ground our outputs in individual examples. And it's a pretty effective way to improve the probability of models, improve translation, and other stuff like this. The disadvantage of doing this is that it provides, it kind of adds an extra component of the model. It adds extra kind of hyperparameters like lambda and things like this. So it is a little bit finicky and it doesn't work in all situations. And so another method that we proposed by Amanda Birch, who gave the previous lecture on generation in this class, is unlimiformer. And basically what unlimiformer does is it notes that attention itself is an inner product search, and it does top K attention. And the way we do this is we first process the input with a sliding window, and then perform attention using a vector index. So if we have a really long input that we want to encode, what we do is we first encode chunks. So we encode, for example, AB, then we encode CD, and we encode EF. We concatenate them together into a big index of one long input. So in a way that this is similar to what they did in the KNN-LM, concatenate all of these embeddings into a single input. But the difference is that this is done with the values that we are attending to, as opposed to just the final layer. And the interesting thing about this is now we have an index of one long input. And when we want to do our next version of attention, we do KNN search from the query. We take the retrieved hidden states, and then we just do attention over them. So the nice thing about this is in the extreme case, this makes no changes to the model. What I mean by this is, let's say our input was small enough that we could encode it in only a single chunk. And for KNN search, we also did KNN search. We did, exact KNN search over all of the embeddings in the chunk. In that case, this would just be normal attention. It's exactly the same as normal attention. However, there are some approximations that go into here, like when we encode chunks, they might not be exactly the same as if we encoded the entire thing together, and we're also chopping off some of the values with very low kind of inner products. And so because of this, there are some approximations being made, but in the extreme case, if we made no approximations, this would just be exactly the same model as we were using before. So I find this pretty attractive, and empirically it gives very good results over long distances. And we can always make our approximations better and improve this model as well. So I think this is an attractive method that you might be interested in taking a look at. Okay, for the final part of this, I'd like to talk about long context transformers. And these are models that are explicitly trained in a way that allows you to attend to longer contexts in an efficient manner. So one way that we can train over longer contexts is just append all of the context together. And in fact, shortly after transformers came out, this paper by Vojta et al. Demonstrated that doing this can learn, interesting document level phenomena. So it can identify when multiple words refer to the same thing or co-reference and other things like this. However, the problem with transformers is that computation is quadratic in the sentence length, because you're multiplying all of the query vectors by all of the key vectors. And that basically causes a big problem if your sequences become very long. So if we go back to what we did in RNNs from the very beginning of the class, in RNNs, they don't have this problem because computation is linear in the length of the sequence. You just pass along the RNN state, and every single time you do the same computation over it. So there's no quadratic term in calculating RNNs. Another thing is that when doing RNNs, you can actually pass state infinitely during the forward pass by just calculating the hidden state and then throwing away the rest of the computation graph that was used in calculating that hidden state. And there's no approximation that goes on there. So Unlike in unlimiformer that I was talking about before, where we needed to make approximations, none need to be made in this case. However, there is a problem with doing backprop, because in order to do backprop, normally you maintain the entire, state of the computation graph. And so a common method to fix this is basically you pass along the RNN state from the previous sentence, but you just don't do backprop into the previous sentence. And this is called truncated backprop or truncated backpropagation through time. And this allows you to essentially train models with infinite context, or at least models that can pass along context infinitely, even if you're not backpropping into the encoder there. So, of course, a problem with this over long contexts is recurrence. Recurrent models can be slow due to the kind of sequential dependence. They're not ideal for, running on GPUs or things like that. And this is improved by recent architectures like Mamba and RWKV, which are more conducive to GPU-based training, while still maintaining linear time complexity. And so I'm looking forward to talking about that more in a future class. So actually, if we take this idea of truncated backpropagation through time, this can also be applied to transformers. And there's a really nice paper, Transformer XL, also created by Zahong Dai, who was formerly at CMU. And what this does is this attempts to fix vectors from the previous sentence. So if we have a standard transformer in Transformer XL, normally what we do in the standard transformer is each vector attends back to all of the other vectors in the current context. What Transformer XL does instead is when you have a new segment that you want to do backprop into, you have a new segment that you want to basically train over, you also attend to all of the previous tokens in the previous segment, but you don't do backprop into them. So this is essentially truncated backpropagation through time from the transformer perspective. This is also really nice because what it allows you to do is if you have a multi-layer transformer, it allows you to attend far back. So if you look at the last layer, it's attending to things in the previous context window. But the second to last layer is attending to things in the, not just one context window before, but multiple context windows before. And actually, this allows you to very effectively attend to very long contexts because each time kind of the context expands in an exponential manner. So recently, there's a popular model called Mistral that I'm sure a lot of people have heard about, and this is using sliding window attention, which is essentially the same mechanism proposed by Transformer XL. So this method is still used in very practical systems. Another paper that has been pretty influential in this general area is something called sparse transformers. And the way sparse transformers work is instead of attending to every single previous state, you attend to every n previous states. And what this allows you to do is this allows you to essentially create something like the strided convolutions or pyramidal recurrent neural networks that I talked about earlier. So what this looks like essentially is you have this, like if you have a particular state, it might attend to all of the previous n tokens, but then it also attends to all of the previous kind of m chunks. So you kind of have a combination of local and global attention. Or not local and global, but local and kind of longer range attention. And this can be very effective because you can attend to, much longer contexts with a minimal increase in computational complexity. So another method that's a little bit like this, or it's very similar in spirit, but slightly different in implementation, is something called the compressive transformer. And in the compressive transformer, you also have this idea of a local memory and then a longer term compressed memory. but you have an explicit compression step that directly essentially generates this compressed memory itself. And so this is a little bit more flexible, I guess. It allows you to take all the, relevant things from your local memory and compress it down. So it's another method that's worth thinking about. Finally, there are some very interesting methods that do low-rank approximations of transformers. And so calculating the attention matrix is expensive, but this is a matrix. And because it's a matrix, we can also approximate it with a lower rank matrix. And there's a couple methods that do things like this. The first one is something called Linformer, which adds low rank linear projections into the model at appropriate places. And there's another one called Nystrom-former, which approximates using the Nystrom method, which is based on sampling landmark points. But basically, the general idea behind this is normally we do this kind of softmax over, a very large attention vector. But instead, we can approximate this softmax by having some low rank vectors, kind of like what we used in LoRa, and nonetheless get a reasonable approximation of the softmax used in attention. Okay, so we're nearing the end of what I want to talk about today. And finally, the thing that I'd like to talk about is benchmarks for long context models. And there's a few benchmarks. One very well-known one is something called Long Range Arena. This is a composite benchmark containing mostly non-NLP tasks. And it's definitely used for long sequence modeling, but the results on the Long Range Arena actually tend to diverge somewhat from the results that you get for long distance language modeling. So in addition to this, another benchmark that I personally like and have used a bit is something called Scrolls, which combines together a whole bunch of kind of QA style or summarization style tasks that have very long contexts, including over narratives or books or government reports or other things like that. So you can also take a look at this if you're interested in kind of benchmarking longer range models. Okay, the final thing I'd like to talk about is now that we have retriever models, we have reader models, we maybe even have reader models that can effectively use very long contexts, like the ones that we retrieve over whole documents. How do we effectively use them in our models? So there was a very nice paper by Nelson Liu at Stanford about a phenomenon that was coined lost in the middle. And basically what it does is it demonstrates that many, many different models, including state-of-the-art models, pay less attention to things in the middle of long context windows. And so if we have an answer and we put it in, the first position in a concatenated context or the 20th position in a concatenated context, it tends to attend more to the ones at the beginning or the end. In contrast, the ones in the middle kind of get lost, hence sitting lost in the middle. And the problem with this is, if we are doing something like retrieval and reading, then that's maybe not such a huge problem because we could just put, the highest scoring documents at the beginning that might even be more effective than, concatenating lots of low scoring documents together. But if we want to read a really long document and synthesize something without doing kind of another scoring step, that can be an issue. And also, our retriever is not perfect. So we would like the reader model to do a good job with the outputs that it has. So there are methods to ensure use of relevant context. So of course, better retrievers make more relevant context. You can do, re-ranking or other things like that and only include the context that looks most relevant, or, refine your reader model. But there's also methods that can decide whether context should be used in the first place. So there are methods to decide whether to include passages or not. And also recently we proposed a method to filter down to parts of retrieved passages to have only appropriate content. And this is a model that we called Filco. It basically filters the context down to the most relevant content that we think is appropriate, and that allows us to get better results when it's fed into the generator. So that's all I have for today. Thank you for watching the video, and for people in the class, I'll be happy to take questions on Piazza or during the office hours that I have planned. Thanks a lot.